Okay, so I am going to be talking about the application of AI to music today. And some of you are working with me in the Music Recommenders project. I'm actually not going to be talking about music recommendations specifically. There are going to be some other things, but asking you what some of those other things might be. So how do you think AI can be applied to music? And if you could drop some suggestions in the chat, I'll take a look at them and we can discuss a few. Okay, yeah. So music recommendations, I'm saying that's definitely a huge application. Auto tune, yeah, that's really interesting. AI is definitely used in that. Creating music, yeah, composing music. Song recognition is a big one. Spotify uses a lot of machine learning techniques, AI techniques in their application. Style transfer, yeah, that's a really interesting one. You can do some kind of rearrangements of songs in a different style. That's something that, yeah, that's a really interesting example. Possibly lyrics, yeah, you can do machine learning on lyrics to generate similar ones or actually like write a melody to them or something. These are all fantastic suggestions. So I've just got a little list of them here, and these are kind of more kind of abstract ones. So you could probably get more specific within each of these categories, but automatic composition and arrangement is certainly a huge application of AI in music these days. Transcribing music from recordings, so basically getting notation from an audio file. It's used in some music theory and analysis situations, which I'm more than happy to talk about later on if you're interested. Music recommendation is a big one. And then analyzing and generating expressive musical performance is sort of a new direction that AI is taking in music as well. So with that in mind, and all the things you suggested in the chat, what kind of data do we need for these tasks? And I don't just mean music, like in what form do we need the music data or other data for that matter? Okay, I'm seeing MP3 file. Yeah, definitely. That's absolutely one format that we can have our data in. Any others? You can use either audio data of performances or MIDI data of actual notes. Yeah, both great suggestions. Or there's Wave. Yeah, Wave is another kind of high quality audio format that's a bit higher quality than MP3. Any other suggestions? What about something that's actually not music data, but it's sort of people's data that's music related? Yeah, sheet music is another one. Okay, yeah, these are some great suggestions. So just to kind of go through a list of them, symbolically encoded music notation, so MIDI was suggested in the chat. There's another form called music XML, and I've just given an example of that over here. It's actually a text-based format, but you can use it to generate musical notation. Sound files such as Wave and MP3, scan sheet music. You could use videos of performances as well. And there are many others. You could use people's like Spotify listening history, playlists, things like that. So there are all sorts of options. And then just for reference, this is what a wave file looks like if you plot it. It's a series of amplitude values over time. So I'm going to talk about a couple of applications of AI to music that particularly interest me. One of them is a research project that has kind of just wrapped up and is being published in February. And the other one is another area of music and AI that really interests me, but I'm not actively working on it, but it's tangential to my, it's sort of related to my interests and research interests. So just a little bit about me first. I am Aditya, I'm from London in the UK. I'm studying at Yale at the moment. I'm doing a PhD in music theory with a focus on music perception and cognition. So basically how we perceive music and process it in real time. And before that, I did my master's at Stanford in music science and technology. And I have an undergrad from the University of Cambridge in music. And the main question I want to answer in my research is how much and what kind of musical information do we use when understanding musical structure and forming expectations of what's going to happen next when we're listening to a song. And so one of the research projects that I conducted was about musical structure in performance specifically. And so I've played the violin for a really, really long time, and I've been interested in how violinists move when they play and how that relates to musical structure. And basically, is there some relationship between expressive movement and musical structure? And so I conducted a project during my master's that involved unsupervised learning, which is a kind of one branch of machine learning on motion capture data. So if you remember Hyun's talk yesterday, he was also talking about kind of body markers and trying to find how different poses changed on videos, and I actually did something similar. So during my master's, I recorded a bunch of violinists, including myself. Here I am, using motion capture equipment. So there are these infrared cameras at the back, and I've got these reflective markers attached to my body. So here I am set up to play. And once I collected all these motion capture recordings, I used a technique called principal component analysis. And this is a type of machine learning that's unsupervised. And basically what it does is find the axes or the directions of greatest variance in a data set with lots and lots of dimensions. And it's kind of similar to generating a lot of best fit lines. It's useful because it reduces the number of features that you have in your data. It's something called dimensionality reduction. So if you have tons and tons of things going on, it's useful to just get a small subset of those that actually capture a lot of what's going on, because it might be easier, kind of computationally less expensive. And it generates meaningful new features. So the things that you generate are actually like useful combinations of what you already have, and that's called feature extraction. And so I just have a little example of that on the left. Suppose you have a data set with kind of X and Y dimensions. And essentially, one thing you can notice about it is that most of the variation that you see is in this direction. It's represented by the red line. And then the rest of the variation you see is represented by this green line. So actually, we can transform the original data set into this PCA transformed basis. So we have new axes, PC1 and PC2, and then everything basically falls on this horizontal line. So that's just one way of generating new features that are actually useful. So I did some PCA on the marker positions in 3D space, and I found some cool things. I'm actually just going to skip to this slide. So I'm going to play you the original footage. So there's no sound in this. This is just a recording of actually me playing the violin, just a video footage of that. And when I ran PCA on this clip, I got a number of PCs out. One of them, PC1, is the one that explained most of the variance, the variation in the motion that you see. And it looked like this. And what's interesting about this is that it's side-to-side motion. So really very little of what I'm doing here is related to the instrument technique. It's just my body swaying from side to side. The violin is totally still, the bow is totally still. By contrast, the second principal component, you'll see the motion of the right arm, which is this one if you have the camera's head on. And it's going up and down like this. And so this is kind of or this movement is related to technique. It's string crossing, so moving from one string to another on the violin. And it's pretty interesting that PCA actually generated these motions. I averaged them across a bunch of different violinists, and it got very similar things on each one. But I was mainly interested in the non-technical motion. So this PC1, and then there was a third principal component as well that was interesting. And when I analyzed the data, I found that there was more increase in the non-technical motion around moments of musical resolution, which are called cadences. So you can see here, there are two types of cadence, the local and global. And the global one, there's a much bigger change, especially in the second half, but also in the first half, there is actually a difference between these differences. So yeah, it goes to show that violinists do actually embody the structural salience of the music that they're playing through their expressive physical motion. So that's pretty cool. And if you want to find out more, in a couple of months' time, you can read this research in the journal Music Perception. I'm more than happy to send a copy your way when it comes out. Okay, so moving to another form of musical structure, and how AI can be used to generate music in this case based on existing music that it's trained on. And one thing that you can do is automatic harmonization. And the composer Johann Sebastian Bach, he was a very famous composer. He wrote a number of chorales, which are basically melodies accompanied by three parts in a homophonic texture. And what I mean by homophonic is it's basically one note, roughly speaking, one note in the accompaniment per note in the melody. And the good thing about this is that it's a very kind of stylistically coherent collection of music. Like all the chorales sound reasonably similar to each other. So perhaps computers can learn to harmonize melodies in a similar fashion to Bach. So I'm not going to dwell too much on the sheet music here, but this is what a chorale looks like in notated form. And nowadays, this task has been approached with neural network technology and some even more advanced machine learning technology. But the gold standard before neural networks were really mainstream were Markov models. And so what they were, what they do is they estimate how likely certain sequences of tokens, continuous tokens, so in this case, musical notes, we can call them n-grams, how frequently they appear. And it's a technique that's also been used in natural language processing, kind of classical statistical techniques. And they can be used for various things, so including generating new music, but also determining the likelihood of a musical sequence in a particular style, and classification tasks such as kind of determining the genre, the key of a piece of music, its mood, and so on. And there are a couple of examples here from the research literature in music information retrieval and music theory. Nowadays, however, we do have neural networks at our disposal. And I will say, before I discuss the neural network stuff, that one nice thing about Markov models is that we know exactly how to interpret them. We're literally just counting the number of times certain sequences appear, and so they're really interpretable, kind of nice models that we can use to actually make kind of concrete predictions, even just intuitively. Neural networks don't necessarily provide that for us in the same way, but they are very powerful in other ways, and we're going to look at why that's the case. And one example in particular that was very interesting is called BachBot. It came out about 4 years ago by Feynman Liang and a team of researchers at Cambridge. And it's a recurrent neural network model for generating novel harmonies for pre-existing chorale melodies in the style of Bach. And we've seen RNNs in NLP applications as well. I don't have too much time to talk about the special features of it, but basically it uses LSTM cells, which are really good at figuring out kind of what information to memorize and what information to forget as you're training throughout the course of the RNN. And you can find out a bit more about RNNs on Chris Oler's really great blog. I recommend you check it out. And I'm in fact just going to drop a link to that in the chat so that you can all take a look at it at some point. And you can find the model itself on bachbot.com, which is right here. So in an RNN, just to recap, or maybe this is new information for you if you haven't seen this already, but the value of a neuron in each hidden layer of the network, which is represented by A over here, you calculate that by combining the value of the input neuron, which is X, and the previous hidden layer. So it's feeding in like this. And then you apply an activation function and you get some new values out and you get outputs at each stage, or you can just look at the output at the end. But that's how it looks. This is the rolled up version. This is the unrolled version. And then this is what's happening inside an LSTM cell. As I said, it's pretty complex, but essentially it does a bunch of calculations that determine whether to keep information in memory or forget if it's not relevant. And this helps maintain coherence in the output structure. So with BachBot, we can't really use regular sheet music. So the researchers developed an encoding scheme, which this is the MIDI keyboard, like the MIDI number of the pitch. And then false or true is determining whether it's a note that's tied on from the previous note. So true means it is tied on and false means it's not. And they sort of just go up and down and encode everything. And basically the output of the network that you get is a probability distribution over all of these pitches. So you feed in just the melody, this top line, so this 65, 64, 64, and then you will get some probability distribution over how likely it is that other pitches will appear in the different parts. So, hopefully if it's trained well, then 59 will have a high probability on it, 58 will have a low one, and so on. So the model did really, really well. Like surprisingly well, in my opinion. I can't quite pinpoint why I'm surprised that it did as well as it does, but I think it's because previous RNN efforts in music generation didn't really have that much coherence in the structure of the output, even if they had used LSTM cells or something similar like GRUs called gated recurrent units, which do a similar thing. But I guess partly because Bach chorales are very uniform in their style, very coherent across the whole corpus, across the whole data set, you do actually get fairly consistent harmonizations out. Still not perfect, as we'll hear in a second, but it did well. And actually, something cool happened is that certain neurons in the network became sensitive to different types of chords. And so if you analyze music, one technique that is often used for harmonic analysis is using Roman numerals. And so what the researchers did is they looked at all the Roman numerals of the chords that were being output and saw which neurons in the network were sensitive to them. And so it turned out that there was a neuron in the first layer, neuron 64, that happened to be sensitive to a particular progression that you can see. It's pretty small in here, but it goes from chord 5 to chord 1. And then there is an intervening chord, in this case chord 3, but we can sort of ignore that. So there's a small activation here from 5 to 1, similar there. And then at the end, which is called the cadence, the final point, there's a very big activation. And there's some tiny one over here that I can't quite account for. And then the 151st neuron in layer 1 had a similar sort of sensitivity to a different type of progression. This is from chords 6 to 7 to 6, and that happens again there. I don't see it anywhere else in here, but I guess if it were there, then it would be activated. So it's pretty cool that these neurons were specializing. And that's something that actually happens in the brain as well. Like neural networks are inspired by the brain architecture, and actually certain neurons in the brain are very specialized for certain activities. So this is maybe unsurprising that this happened, given that it did so well. Last thing I'm going to do is just play an example of BarkBot, and I want you to put in the chat how you think it sounds. All right. All right. There we go. So yeah, thanks so much for listening, everyone. And yeah, if you want to share your thoughts about how BarkBot did, in your opinion, in harmonizing Twinkle Twinkle, feel free to put it in the chat. But I'm more than happy to take any questions. And yeah, thanks for listening.